Hello everyone, welcome to the class once again. I hope you all enjoyed the last classes in this chapter, and now we'll be taking the last topic today. In the last class I was talking about heat engines. I developed the equation for heat engine, its efficiency. Today we'll go ahead and we'll understand the refrigerator concept. Before that, let me tell you about Carnot's theorem. Now Carnot's theorem states that for any kind of engine, its efficiency cannot be more than the efficiency of a Carnot engine that already we have studied, that is working between two temperatures. So I will state that the efficiency of any engine, the efficiency of any heat engine cannot be any heat engine working between two temperatures. I already have told you that any engine will be working between two temperature sets. So any heat engine working between two temperatures, cannot be more than Carnot's idle engine. Cannot be more than an idle Carnot's engine that already I have discussed in the last class. Cannot be more than idle Carnot engine. Now efficiency of Carnot engine I have already discussed in the last class. It was actually work done with respect to the heat supplied. This was what I have told you in the last class. And then we have also derived for various processes, the various steps that the gas takes place while taking the heat from one body to and doing some work and then releasing all the leftover heat to the sink. Now today we will be learning the next concept. The next concept, that is the refrigerator. In the last class we have talked about heat engine. It was taking heat from some object, some source, and then it was utilizing some amount of heat to do some work. And then some amount of heat was rejected to the sink. That is what we have studied in the last class. Today we will see the reverse process. You all must have used refrigerator in your house where you keep the things to let it coolify. How does that work? Have you ever imagined that the inner temperature of the refrigerator is quite cool compared to the external temperature? What that refrigerator is doing? It's taking the amount of heat energy from the interior of the refrigerator and releasing it to the outer atmosphere. So you must be thinking that it is disobeying the natural law. We know that from natural law, heat energy can be only transmitted from a body at higher temperature to a body at lower temperature. But what is happening here? Heat energy is transmitted from a body at lower temperature to a body at higher temperature. That is what we observe in the working of refrigerator. How does it work? You see that we all know that a compressor actually does work on the refrigerator to coolify interior. Now before that, let me just give you a quick recap of what we have done in the heat engine. In the heat engine case, what we had a source at a particular temperature. Let's say the temperature is T1. It supplied certain amount of heat to a working substance. You must be knowing about working substance, that is the gaseous system that we have taken. This working substance, what it did some amount of work and then it rejected some amount of heat energy to the sink. This is what we have learned in the last class. Now the amount of work done that we have observed, that was Q1 minus Q2. You can see the balance. This amount of heat energy that was taken from the source, that is Q1. From Q1, Q2 amount is rejected and the leftover released, that is Q1 minus Q2, this is taken as the work done. This much is the amount of work done. This is utilized in running the machine. Just reverse of this is we will be having the refrigerator. Let me talk about refrigerator. We all know that how refrigerator works. Refrigerator will take some amount of heat energy from a body at lower temperature, and then the compressor will do some work on the working substance, and then some amount of heat energy will be rejected to the external surrounding. Let me show you the reverse way. Suppose we have, this is the actually from where the heat energy has to be taken. So let me take this as sink was here, from where, now this is the place from where heat energy will be taken. So let me go ahead and let me mark here that we are going, and let's say this is the heat absorber. Or if you can go ahead with the sink, it will be sink also be the more better one, more better term, because we have the sink here to which heat is rejected. So let us go ahead with the sink term, that will be far better. Heat absorber, that is not suiting to this term. So let's use sink. Now from sink you are taking some amount of heat energy Q2. Q2 amount of heat is taken. There is a working substance. There is a working substance which actually on it work has to be done. On it work has to be done, and it will reject Q1 amount of heat energy to the external surrounding. Q1 amount of heat energy to the external surrounding. I am just moving out of this diagram, just take it that it's external surrounding, Q1 amount of heat is rejected. Now that means the amount of work that has to be done on it, that would be Q1 minus Q2, just opposite of the heat engine, sorry. This much will be the work done on the working substance by the compressor. We all know that compressor is actually in the refrigerator that does the work on the working substance. We can see that from the sink, Q2 amount is taken over by the working substance. It will release Q1 amount of heat energy to the external surrounding, and we can see that the amount of work done from here, that will be Q1 minus Q2. Easily you can absorb. You can easily observe that as I have written here. So what do you take note till here? I'll start from the other end. The first question is, water of volume 2 liter in a container is heated with a coil of 1 kilowatt at 27 degrees Celsius. The lid of the container is open and energy dissipates at rate of 160 joule per second. In how much time temperature will rise from 27 degrees Celsius to 77 degrees Celsius? A 8 minute 20 seconds, B 6 minute 2 seconds, C 7 minute, and D 14 minute. This question has been asked in one of the previous examination of JEE. Let's read the question and let's try to analyze what things have been given and what is required from the question. Which method we can actually utilize to solve this question. You see here, water of volume 2 liter. We all know that in our heat equation, we all need the mass of water. 2 liter of water, that means we can take that its mass will be approximately 2 kg. We'll be using 2 kg for it. 2 liter in a container is heated with a coil of 1 kilowatt at 27 degrees Celsius. Now see here, the coil is of 1 kilowatt. 1 kilowatt means 1000 joule of energy will be actually taken up by water. Now the lid of the container is open and energy dissipates at the rate of 160 joule per second. That is, net heat energy obtained by water in this case will be net heat energy obtained by water will be 1000 minus 160, quite simple. Net heat energy obtained by water will be 1000 is the heat energy transferred by the heater. So 1000 joule per second, that is what we can say, minus 160 joule per second, that is radiated. So this comes out to be 840 joule per second of the heat energy that is acquired by water. So 840 joule per second. So first thing we got the rate at which water acquires heat energy, that is 840 joule per second. Next you see the lid of the container is open and we have used this. In how much time temperature will rise from 27 to 77 degrees Celsius? The rise in temperature is asked. What is the time? Now see the heat energy required by the water, that will be mc delta T. So first of all, heat energy required will come out to be m specific heat capacity of water and delta T. This is what we have to use. Mass, that is not given directly, but we can use that since volume is given 2 liters. If volume is 2 liters, certainly we can use mass as 2 kg. So keep mass as 2 kg and let's say time taken is T. Let time taken is T. So the formula that we can use, let time taken be T. The formula that we shall be using, that will turn out to be 840 into T will be equal to, because 840 joule per second should be equal to mCW delta T. From here, T comes out to be mCW delta T divided by 840. Clear? Not too tough to understand this. Mass you can use as 2 kg. CW, specific heat capacity of water, we know that it's 4200 joule per kg per degree Celsius. That is what we know. So 4200 joule per kg per degree Celsius, 2 kg is the water, multiplied by difference in temperature, that is 77 minus 27 divided by 840. This turns out to be 2 into 4200, we can cancel out this 10 and 10. Rest you see 42 into 2 times it will go, and 10 you are having here. So you will be having 10 by 2, you will get 5. So let me use here the value as 5. Quite simple, we can use this 84 and 420 will go 5 times. And finally, you will be having, this is divided by 1, you will be having this and multiply with 50. So this comes out to be 500 second. This is what we can obtain. Now we have did the first part of the question. We need to just answer in the required units, in what units the answer is given. So what you do, take note till here. Let me start at the other end. Take note till here. So I believe that you have understood how we have obtained this 500 second. Now clearly we all know that the answer is given in minutes and second. So 500 second, that will come out to be 500 divided by 60. This will come out to be 8 minutes and 20 seconds. This will come out to be 8 minutes and 20 seconds. So let's check the given option with this result, 8 minutes and 20 seconds. You can clearly see that option number A is 8 minutes 20 seconds. That's the right answer. Rest all options are incorrect. This is what we can understand how to solve such kind of question. Easy question, a case of thermodynamics, a case of heat transfer, a case of calorimetry. That is what we have learned from this exercise. Just let me clear the board. And I hope that you have watched each of the class of this chapter. A very important chapter. Questions can come in various competitive examination from this chapter. Question number 2. 2 kg of ice at minus 20 degrees Celsius is mixed with 5 kg of water at 20 degrees Celsius in an insulating vessel having a negligible heat capacity. So need not to worry about the calorimeter, need not to worry about the vessel, need not to worry about its heat capacity. Calculate the final mass of water remaining in the container. It is given that the specific heat of water and ice are 1 calorie per kg per degree Celsius and 0.5 kilocalorie per kg per degree Celsius for ice, while the latent heat of fusion of ice is 80 kilocalorie per kg. This is what has been given. So the final mass of water in the container we need to find out. A 7 kg, B 6 kg, C 4 kg, D 2 kg. Now the case is very simple, and before that let me write down the given specification. It says that the specific heat of water and for ice is 0.1 and 0.5 respectively. So CW of water is 1 kilocalorie per kg per degree Celsius, and we are also given with specific heat capacity of ice is 0.5 kilocalorie per kg per degree Celsius. This is both data that has been provided. Next thing you see, it says that the latent heat of fusion of ice is 80 kilocalorie per kg. 80 kilocalorie per kg. So latent heat of fusion of ice, let me write this as L of ice is equal to 80 kilocalorie per kg. That means, what does it mean 80 kilocalorie per kg? That means you need to supply 80 kilocalorie, you need to actually take out 80 kilocalorie of heat energy from water at 0 Celsius to convert it into ice at 0 Celsius, or when ice melts it will absorb 80 kilocalorie of heat energy at 0 Celsius to convert into water at 0 Celsius. Now first of all, you see that what things are provided. You are provided with ice at minus 20 degrees Celsius.
First of all, this is that has been given. You see this, having a 22 kg of ice at minus 20 degrees Celsius. So we have been given with mass of ice is 2 kg initially, that has been given to us. Now next thing you see is mixed with 5 kg of water at 20 degrees Celsius in an insulating vessel. 5 kg of water. So next thing we have been given with water, and mass of water is given as 5 kg. The temperature is 20 degrees Celsius. Both temperature magnitude is same, but signs are opposite, minus 20 for ice and plus 20 for water. Next thing you see, calculate the final mass of water remaining in the container. So what will happen in the process if both are mixed? We are mixing both the two. If both are mixed, ice is supplied to water, so what thing will happen? Water temperature will start decreasing, ice temperature will start increasing. That is what we can actually think of. Now, what will be the final temperature of the system? We are not aware about what is final temperature of the system. So let's say, because since either ice is converting into water, okay, that is what we can say. So first of all, if ice, let's say the temperature attained is 0 degrees Celsius. So what we can comment after this? So the final temperature is 0 degrees Celsius. So heat gained by ice to reach from minus 20 to 0 degrees Celsius. Heat gained by ice. Heat gained by ice to reach from minus 20 to 0 degrees Celsius. Heat gained by ice to reach 0 degrees Celsius from minus 20 degrees Celsius. Let's check it, how much heat is gained. So for this process, the heat acquired will be delta Q1 is equal to mass of ice multiplied with specific heat capacity of ice multiplied with change in temperature. Mass of ice is 2. C of ice, specific capacity of ice, if you see, that's given as 0.5 kilocalorie per kg per degree Celsius. 0.5 kilocalorie, so 10 to the power 3 per kg per degree Celsius, not a problem. Delta T will come out to be 20. I am using directly 20, 0 minus minus 20, you will get 20. So on solving this, you see 20 into 0.5, that will give you 10, 20 to 0.5 will give you 10, and then 10 into 2, 20, 20 to 10 to the power 3, that is the first thing you will be obtaining, 20 to 10 to the power 3 calorie. This is the heat energy taken by ice to reach to 0 degrees Celsius. What I will do for systematically conversion, I will also mention here each step that has taken place. So we have ice, its temperature has been raised to ice at 0 degrees Celsius. So during this process, the heat energy that we have actually supplied to it, that was 20 to 10 to the power 3 calorie. Next thing, how much heat energy water would actually release in lowering its temperature from 20 degrees Celsius to 0 degrees Celsius. Heat energy released by water, heat energy released by water, which is at 20 degrees Celsius to reach at 0 degrees Celsius, released by water. Heat energy released by water to reach from 20 to 0, because it's going to release heat energy to reach 0 degrees Celsius from 20 degrees Celsius. For this, you see what you need to do. Heat energy released by water, that will be again delta Q2, that is mass of water multiplied with C of water multiplied with change in temperature. In this case, you apply this, delta T is different here, delta T is different here. Mass of water is given as 5 kg, so I am using 5 multiplied with specific heat capacity of water, that is 1 kilocalorie. So 1 into 10 to the power 3 multiplied change in temperature, again that's 20. So for this it will come out to be 2500 10 to the power 5, or 10 into 10 to the power 4 we can write, since we are writing in 10 to the power 3. So we can write 100 into 10 to the power 3, that will be more better. 100 into 10 to the power 3 calorie. This much is the amount of heat energy actually released by water to reach 0 to Celsius, 100 into 10 to the power 3. So what I'm going to do, I'm going to make one more curve to actually explain the situation. Since we have less space here, I'll just make some more space. Delta Q1 was given as 20 into 10 to the power 3 calorie. Now for water conversion, what we have obtained for water conversion, I'll use a different color. Water at 20 degrees Celsius to reach at 0 degrees Celsius. Water at 20 degrees Celsius to reach at water at 0 degrees Celsius. For this case, the heat energy actually released by water, that came out to be delta Q2, and that came out to be 100 into 10 to the power 3 calorie. Now try to understand, to reach 0 degrees Celsius, ice needs 20 to 10 to the power 3 calorie and water has released 100 into 10 to the power 3 calorie. That is what we can see up till here. Now further what will happen? Either ice gets converted into water, water gets converted into ice. Let's see that. Before that, we have actually completed the part of the board. You do take note till here. Let me start at the other end. Take note till here. Question number 1. Starting with same initial conditions, an ideal gas expands from volume V1 to V2 in 3 different ways. The work done by the gas is W1 if the process is purely isothermal, W2 if purely isobaric, and W3 if purely adiabatic. So we are given that there are 3 processes, the expansion takes place and it is expanding from volume V1 to V2. The work is W1 if the process is purely isothermal, it's W2 if it's purely isobaric, and W3 if it's adiabatic. So what we're going to do, we're going to see in which the work done is maximum and how the work done is related in all the 3 scenarios. So first of all, let me show you in the 3 cases, if we draw a PV curve, here I am drawing volume, here I am drawing pressure. If we draw a PV curve, let's say since the gas starts at volume V1, the pressure is P0. Let's say the pressure is P0 and it starts at a volume V1. So in the first case, you see it expands, the work done by the gas is W1 if the process is purely isothermal, W2 is purely isobaric. So W2 if it is purely isobaric, that means there will be no change in pressure. So no change in pressure. So let me show you here, this is the first work done. This is V2. Next thing, in the first case you see it's purely isothermal, in the third case W3 is purely adiabatic. In adiabatic, I have told you the slope will be more compared to isothermal. So what you do, for isothermal you should draw the curve in this way, this will be W1, this is the case for isothermal, and here we have, this is the curve for isobaric, and next for adiabatic process, the curve will be somewhat like this. This is the curve for it will be adiabatic, isobaric already we have done, this is adiabatic. So work done during this, the third case is W3, that is what that has been given. Now it's required to compare the work done in all the 3 processes, W2, W1, W3. Clearly from the graph, if you see, maximum work is area under the curve and maximum work done will be max for W2. That is when the process is isobaric, in that case only the work done will be maximum. Next you see the second, it will be W1 for isothermal process and the minimum work will be done in the adiabatic process. So you need not to write the equations for the work done in all the 3 cases. You can just draw a curve, a relative curve, which can give you an idea how will be the work done related in all the 3 cases. It's a very good question, learning question, which you can actually take it and which you can learn how the work is related in all the 3 cases. So W2 is maximum, then we have W1 and then we have W3. W2 is greater than W1 is greater than W3. First one, option number A, that matches with the right answer. Next, B will be incorrect. C, W1 is max, no. D, W1 is max, no. Maximum is W2, that is what we are getting. And this is the way that is given to us so that we can get the relation between the three work done in the three kind of process that we can see. Hope you have got to know how to solve such kind of questions. A good question based upon how to evaluate the relation between the work done in all the three cases. Let's go to the next question of the class. Question number 2. A monoatomic ideal gas. It's a monoatomic ideal gas initially at temperature T1 is enclosed in a cylinder fitted with a frictionless piston. The gas is allowed to expand adiabatically. Adiabatic, that means there is no heat change, to a temperature T2 by releasing the piston suddenly. It's an adiabatic process. If the L1 and L2 are the lengths of the gas column before and after expansion respectively, then T1 by T2 is given by. T1 by T2 we need to compare, and volume is what that has been given to us. So first of all, for adiabatic process, we know that you can write for adiabatic process Tv power gamma minus 1 is equal to constant. This is what we can write. Tv power gamma minus 1 is equal to constant. So we can write that temperature is inversely proportional to 1 upon V power gamma minus 1. This is what we can write. Now it says that an ideal monoatomic gas initially at temperature T1. Let's say the initial temperature is T1, that is provided, and the initial volume is V1. So we can write that T1 will be proportional to 1 upon V1 power gamma minus 1, and T2 will be inversely proportional to 1 upon V2 power gamma minus 1. This is what we can write. Now if we take the ratios T1 by T2, because here it's required the value of T1 by T2. So T1 by T2 ratio will come out to be, that will be equal to, what do? You take this V1 will move, V1 will be in the denominator, so bring V1 here, and V2 will go in the numerator, and power gamma minus 1. This is what we know. Now it's given that it's a monoatomic gas. For monoatomic gas, the value of gamma is 5 by 3, that is what you can use, 5 by 3. So T1 by T2 will come out to be is equal to, now for volume V2 by V1, you can write that as A into length. So A into L2 divide by A into L1 power 5 by 3 minus 1, you get that's 2 by 3. So it will be L2 by L1 divided by 5 by 3 minus 1, you will get 2 by 3. This is the answer for the ratio of temperature in the two cases, L2 by L1 power 2 by 3. Let's go ahead and check T1 by T2, L1 by L2, no, it's not L1 by L2, it's not L1 by L2 anything, L1 by L2 power 2 by 3, no. C L2 by L1, no, this is not we are getting, and D L2 by L1 power 2 by 3, yes, this is the answer that we are getting. A very good question to relate, because here we know that adiabatic process we need to use this equation. You will be confused that adiabatic constant, to use it, adiabatic process, we don't know that PV power gamma equals to constant. From there, PV power gamma equals to constant, you can actually derive this result, and then you can proceed accordingly to reach to the final calculation of T1 by T2. Hope that you are getting, with each of the question we practice, you are enhancing your skills and you are getting to know how to solve such questions. Let's go to the next question of the class, question number 3. In a given process of an ideal gas, dW equals to 0, that is work done is 0, and dQ is less than 0, then for the gas the temperature will decrease, the volume will increase, the pressure will remain constant, the temperature will increase. First of all, it's given that let's use the concept of first law of thermodynamics. The first law of thermodynamics says that dQ is equal to du plus dW. Now dW is 0. Given that dQ is less than 0, that means heat will not be supplied, rather it will be extracted from the gas. dQ is less than 0 provided. So if dQ is less than 0, therefore du will be less than 0. We all know this. So internal energy is going to decrease. Internal energy is going to decrease, that is decreasing with time, it decreases. Internal energy decreases. So if it decreases, what does that mean? What does it imply? It means that since internal energy is directly proportional to temperature, U equals to NCVT, that is what we know. U is equal to, or you can write U is equal to NF by 2 RT. F is the degree of freedom. This is what we know. So U is directly proportional to temperature. Internal energy decreases, that means temperature has to decrease. It has got a direct connotation with temperature, it has to decrease. So we all can comment that temperature decreases. So it's a single choice question, the temperature will decrease. Yes, option number A is the correct response. B, the volume will increase. No, we cannot comment on, because the gas dq is less than 0, there is no work done. The volume is going to remain constant. The pressure will remain constant, that's not required. We are holding the piston at the same position. Pressure will not remain constant. The temperature will increase. We all seeing that temperature decreases. So even this is incorrect. Rest 3 options we have logically come to the conclusion B, C, D are incorrect and A will be the only correct option here. Let's switch to the next question and hope that with each question you are learning the concepts in a better way. Next question of the class, question number 4. An ideal gas enclosed in a vertical cylindrical container supports a freely moving piston. It's a freely moving piston of mass m. The piston and the cylinder have equal cross-sectional area. When the piston is in equilibrium, the volume of the gas is V naught and its pressure is P naught. So volume and pressure is given. The piston is slightly displaced from the equilibrium position and released. It's displaced and released. Assuming that the system is completely isolated from its surrounding, the piston executes a simple harmonic motion with frequency A, B, C, D. You can check the options. It's given in terms of area and then P naught, V naught, M. It's also given in terms of gamma also. You can see it's gamma, your A into gamma. Think that it's gamma, it's multiplied. It's not in the suffix. Next thing, and here also gamma is in suffix. So how to find out? First of all, let me tell you it's a case of adiabatic process, and you can see, because see what is happening here. First of all, there is a piston. There is a piston, there is a cylinder. Let's say this is the case. This is the piston. The pressure is P naught, the volume is V naught, the pressure is P naught, and the volume is V naught. We all know that, dP by dV is equal to minus gamma P naught by V naught. This is what we know. Next thing you try to understand, at equilibrium, what we can write? At equilibrium, we can write that P naught into A, pressure into area, is equal to M into G. This is what we know. In equilibrium, this will be holding. Next thing, after this, how to proceed? We all know that force is equal to minus K into X. If we from any means we come to know that, what will be the value of force when the piston is displaced? See, the piston is displaced, the external force, the extra force will come out to be dP into V. dP into V. So F will come out to be dP into dV. That is what you are going to get. That will be the value. Now, how to find out this dP into V? First of all, dP will come out to be, you can write F as dP, that is minus gamma P naught V naught into dV minus gamma P naught V naught into dV, and here you have V. That is what you can actually express. So finally, you will be getting this as minus gamma P naught by V naught. dV will come out to be A into dx, and V will be equal to A into length. That is what you can actually comment, because finally you will be getting this as A into length L, and here you will be getting dV as A into dx. Or let's keep it as, it's not required, let's keep it as V naught. V naught, that is actually given, so let's keep it as V. So what do you take note till here? Let me start at the other end, take note till here.